Hello everybody, welcome to section 7.2, and in 7.2 we're going to talk about some characteristics of ionic compounds that are dissolved in water, and that's where they can become an electrolyte. So in water, if you place an ionic compound and some other compounds in water, strong electrolytes are going to produce ions, and when they produce ions, that gives them the capability to conduct an electrical current. And so since they can conduct an electrical current, we call them electrolytes. A weak electrolyte just produces a few ions. Non-electrolytes don't produce any ions. So your example down here, if you've got a salt, which is an ionic compound, when you dissociate those into the ions, it will literally form a circuit, and it'll give you enough power to light up a light bulb. If you have a weak acid such as hydrofluoric acid, an acid such as this, all of the hydrofluoric acid does not dissociate. Some of it does, but it doesn't completely dissociate like the ionic compound over here does. And so that forms a weak electrolyte, and so it will provide enough ions maybe to give you a little bit of energy, but not to completely, light it up. A non-electrolyte, which is usually like a molecular compound, such as a sugar, such as sucrose, which is what you put in your sweet tea down here in the South, that will not conduct electricity because there are no ions in which to flow. Okay, so you can't pass those electrons on. So strong electrolytes are going to completely dissociate and give you lots of ions so you can conduct electricity. Weak electrolytes will dissociate some, but not completely, and non-electrolytes will not produce ions in solution. So when you dissociate a strong electrolyte, you're going to basically separate it into the positive and the negative ions. And so since you've done this, we call this now, it's in an aqueous or aqueous solution. And so you formed the sodium and the chlorine. Now they are sodium ion and chloride ion, and we use the AQ to show that we have dissolved this solid in water. Notice that the arrow here goes one way, and that means that it has dissociated this and removed the sodium and the chlorine from each other, and so now you have sodium ions and chloride ions, and they're not going to go back. Okay, so see if you can complete this for calcium chloride, which is another salt. Calcium chloride, which is a solid, when you put it in water, is going to produce ions. And you remember how you can tell? You can look and see what column they're in to see what their charge is going to be. Okay, remember that they're going to dissociate one particular way, and so you have to see what their charge will be. So with calcium, it takes 2 chlorines to form this formula with calcium to form calcium chloride. Calcium chloride, which is in the second column, forms a +2. Okay, so that part is correct. All right, then would you have a Cl2 minus, or would you have 2 Cl minuses? Well, you'd actually have this, because if you look, chloride is in group 7, and that means that it's a -1. So you've got a calcium, which is a +2, and a chlorine, which is a -1 ion. All right, see if you can do the second one. Remember that PO4 is a polyatomic ion. You only have one of these that's going to require 3 potassiums. So if you know the potassium charge, then you can tell what the charge is on the phosphate. Put me on hold if you need to. Okay, so if you did your calculations correctly, you know that since there's 1 phosphate and 3 potassiums, potassium is a +1, so you got 3 K pluses, so you only have 1 PO4, so it must have a 3- charge. If you don't remember how this works, go back and review your stoichiometry, okay, because that's where we learned how to do this. Alright, so a weak electrolyte, we said, dissociates only slightly in water. And so when we write dissociation of a weak electrolyte, what we're going to do is we're going to have it, everything will be aqueous, okay? And you will get a plus and a minus here for your HF. But this time, what are we going to do? We're going to put the arrows going both ways, because basically what is happening is you're dissociating the HF to the ions, but the ions can also recombine and reform the HF. So you never get the complete dissociation like you do with a strong electrolyte. So you never have everything as an ion. Non-electrolytes, they can dissolve as molecules in water. They can be hydrated in those spheres of hydration, but they do not produce ions in water, and so they do not conduct electricity. And we said the example we were using was the sucrose. So notice that this does not split apart. It just merely goes from the solid form of the sucrose to the aqueous form. So I just put table 7.4 in here, which is also in your book, because it's giving you everything you ever wanted to know about solute classification, how they dissociate, if they form ions or molecules, if they conduct electricity, and then some normal examples of some of these. So when you're doing this and you're producing ions in water, depending on how many ions you're going to end up with, we call those equivalents, okay? And so if you have basically it's the charge. So if you have a sodium ion which has a +1 charge, it will produce 1 equivalent per mole in an aqueous solution. Something like calcium, which has a +2 charge, is going to give you 2 pluses, okay, and so that'll be 2 equivalents. See how this does? And then iron, Fe3+, gives you 3 equivalents. And it doesn't matter if it's a negative or a positive, it's just the numeric value of the charge. That's how many equivalents per mole you have. So you may have seen this if you work in the healthcare industry, or if you've had a class in it, IV solutions and things like that. You often see them stated as milliequivalents per liter. And Ringer's solution, for example, which is a pretty common IV solution to replace electrolytes, you would have 147 milliequivalents per liter of sodium, 4 milliequivalents per liter of potassium, 4 milliequivalents per liter of calcium, and 154 milliequivalents per liter of chloride. And so you must have equal negative ions, which are called anions, with your cations, your positive ions. So if you have 154 milliequivalents per liter of positive ions, they must be offset with 154 milliequivalents of negative ions. In this case, you just use a chloride salt. And this is, you're not going to be tested on this, okay, but this is just to put this in perspective for you about, for example, normal saline solution, which is 0.9% sodium chloride solution, because it is that is very close to what your actual fluid is in your body. And so when we replace fluid, we use that 0.9%. Potassium chloride and 5% dextrose. The electrolytes are going to be 40-40 for potassium and chloride. And if you're wondering where a lot of these numbers come from, they come from what should be normal in the body. The Ringer solution has several different ones. Also, 5% dextrose with lactose, with lactate, lactated Ringers, and so all different ones. Okay, so it just depends on what's going on with the patient and what they're deficient in. Electrolytes found in blood plasma: sodium, potassium, as we said, magnesium, calcium, chloride, bicarb, phosphate, and then proteins. And proteins are not going to be electrolytes, are they? Typically, they can be charged, but they aren't really electrolytes. So in 1 mole of Fe3+, how many equivalents would you have? Well, you'd have 3, right? Because it's the charge on it. Now, if you have 2.5 moles of SO4 2-, how many equivalents would you have? Well, if you just had 1 mole, you'd have 2, right? But instead of 1 mole, you have 2.5. So instead of just 2, you have 2.5 times 2, so you'd have 5 equivalents. You can do this last one yourself, but let me ask you a question while we're talking about this. I was talking about milliequivalents when I was talking about IV solutions. So this, in order for us to have 3 milliequivalents, we would have to have what? A millimole. And you'll see millimoles when you have to have these low concentrations, these milligram concentrations, because you don't have grams of a lot of these trace minerals. And if you worked that one, you should have gotten, since sodium is a plus, that you'll have 34 milliequivalents and 34 milliequivalents of your negatives, so that they will cancel out. Alright, and that's the end of 7.2. Very painless so far. The hardest thing we've had to do is multiply 2.5 times 2. So those of you who don't like math too much are happy so far. So I will see you all again for 7.3.